Yo, all right, let's take a look at this next optimization problem. It says consider all lines in the xy plane that pass through both the origin and a point xy in the graph of y equals x squared minus x plus 16, but only for x values between 1 and 8. It says the figure below shows one such line and the graph of the parabola. It says find the point of the curve that minimizes the slope. So here we go. All right, so we're looking at this and we're like, okay, first thing we're writing down is that we want to minimize the slope. So now I hooked you up, I gave you the picture, and we're trying to minimize the slope of this line. All right, which I guess seems a little awkward when you just look at this picture, because if the line goes here, there'd be a steeper slope, a greater slope, and the further you go to the right, you're thinking it's going to get smaller. So you might think that it would have to happen at that right endpoint when x is 8. So hold on to that thought, and let's just go through the process, which is, all right, if I want to minimize slope, I need to come up with a slope formula, right? So I need a slope function. So slope, which I'll just say s, is going to equal, well, what would the slope of this line be? Well, it's change in y over change in x. So it'd be y minus 0 over x minus 0, which that's just going to be y divided by x. So that's pretty easy. So now, likewise, or I shouldn't say likewise, but the same deal as always, right? You need to get your function in terms of one variable, just makes the world a lot easier. So if only you knew what y was, but you do know what y is on this curve. It's this parabola, right? So I can rewrite this as my function s of x. It's basically going to be x squared minus x plus 16, and then all over x, right? So now that's a quotient. Nobody likes quotients, right? So we can spruce this. You can rewrite this as x to the negative 1 times all of this and then distribute, or you can basically just divide it. And when you do that, x squared over x is going to be x, minus x over x is minus 1, and 16 over x is 16 over x, but maybe I'd rather write that as plus 16x to the negative 1, right? So that's just breaking up the numerator over addition and subtraction. It's basically just dividing. Remember, this x divides all three terms up top. Don't you dare just cross out one pairing, okay? So now there it is. And so you're like, all right, well, my intervals kind of was picked for me here, right? So everything is between 1 and 8. So I don't have to think about this one. If they didn't give me an interval, I guess I'd have to view this as negative infinity to infinity. But luckily, they gave me an interval. So I'm good to go. So this is 1, 8. And so now, all right, I don't have a polynomial, so I can't just so quickly say that my function is continuous here, the one I'm trying to minimize, but it would be. And that's because I know that the only value of x that's going to break this function would be 0, because I'd have 16 divided by 0. And that's not in this interval. So we're good to go. So let's go ahead and take the derivative now, right? So s prime of x, that's going to equal, let's see, 1 minus 16x to the negative 2. So I got to get my critical points. So I'm going to set this equal to 0. And when I do that, I'm going to factor out an x to the negative 2. Right? So now if I factor that out, x to the negative 2 times what gives me 1. That would be x squared, right? Because negative 2 plus 2 is 0. X to the 0 is 1. And here I get minus 16. And so now I'm going to get that s prime is undefined at x equals 0, right? So it's potentially a critical point here. It's a point of non-differentiability, but 0 is not in the interval, all right? So this is not in my interval, so not in 1 to 8, so I don't care about that. And then from this guy over here, when I set this factor equal to 0, I'm going to get x equals plus or minus 4. And so again, I don't care about the negative here. So this one there is not in the interval 1 to 8. So then the only critical point that I have here is 4. So now what do I want to do? Well, I have a continuous function on a closed interval. So that means the extreme value theorem is going to guarantee me an absolute max and an absolute min. So all I need to do now is test my candidates. All right, so I should be writing some of this out, but I'm going to streamline this video a little bit. I'm just going to get after it. So I'm going to write, all right, let's test candidates. And you test them in the slope function. So it's going to be x and then s of x, and go ahead and do this. So we have to test our endpoints, 1 and 8. and then we have to test our critical point, okay? So let's get after it. So let's see what we can do here. So if I test 1, and again, I'm testing it in S of x, 1 minus 1, that's 0. And then 1 to any power is 1. So 0 plus 16, that's going to be 16. So you get a slope of 16 there, okay? All right, so now if I test 8, 8 minus 1 is 7. 8 to the negative 1 is like 1 over 8. 16 over 8 is 2. 7 plus 2 is 9. That looks pretty decent. And now I'm going to test 4. So 4 minus 1, that's going to be 3. 4 to the negative 1 is like 1 over 4. So 16 over 4 is going to be 4. 4 plus 3 is 7. So I get a minimum slope of 7. All right, so this is my min here. So there is a min slope of 7. All right, now it said what? It said find the point. Find the point. So we'll say at the point. Now, what did we get here? Well, we got x is 4. We'd have to go ahead and figure out what the y value is at that point. So I'd have to plug 4 into here. All right. So 4 squared is 16, minus 4 is 12, plus 16, that's going to be what? 28. So at the point 28. All right. So pretty good, pretty neat problem. Again, now that you're like, why? That doesn't make sense. It should be at 8. Well, let's take a look at the graph of this thing. All right, so here we go. We have the graph of the parabola. I kind of colored in from 1 to 8 because that's all I'm looking at. The green line is the line that is going through the parabola that's going to intersect at some point. And now you can see here, I can kind of move that point around. So now what happens here? So obviously these slopes are positive values. And then I work my way over to 7. All right, a slope of 7, so 4. So this is the point 4 here. You can see, okay, that's the answer we got. And why does that make sense? Well, because you fall off the curve after that, right? So you're only kind of intersecting the curve between really 1 and 4 here in terms of this green line. All right, so it actually now, I get it. It kind of makes sense. So the minimum slope ends up being, if you think about it, the slope of the tangent line at x equals 4. It's when that line actually becomes tangent to the curve, which would have been another way to ask that question. All right, so hopefully that makes sense. The only thing I really didn't do is I didn't spell out or say why the extreme value theorem applies. Maybe I should say that. Since the function is continuous on the closed interval, the extreme value theorem applies. And then the rest is as is. All right, good stuff. Optimization. Be good.